So today we are going to design a slab. Okay, so we have a question and I have just taken the details, important details from the question. You have the question. This is a dimension 4 by 6 meter inside dimension. Inside dimension means this is the room. Okay, walls will be like this. Okay, so inside dimension 4 meter is this dimension and 6 meter is longer dimension. Okay, inside dimension, and we are having 200 mm thick wall. This is 200 mm thickness. Okay, and this is important when it comes to two-way slab. This will determine what type of slab it is. Okay, so we'll talk about it later. Free to lift up. This slab that we are building on over this 4 walls is free to lift up. There are no bonding with the masonry wall. Okay, so it is that detail is important. Free to lift up. Okay, so we understand that it is a simply supported slab. Simply supported slab. Okay, there is no bonding, so that we don't have to design a particular extra reinforcements at the 4 corners or anything. Okay, and load is 4 kN per meter square. We have M20 concrete and Fe 450. Okay, so we are getting into the designing of slab, and we all know, as we all know, we have the ratio Ly by Lx, where Ly is larger span and Lx is smaller span. Okay, so in this case it is 6 by 4, and we all know that if Ly by Lx is greater than 2, it will be one-way slab. Okay, we are determining whether it is greater than 2 or less than 2. Okay, so if it is greater than 2, it is one-way slab, or not. If it is less than or equal to 2, it is two-way slab. Okay, as simple as that. So in this, we already know it comes about 1.5. that means it is less than 2. Therefore, two-way slab is to be designed. Okay, so we have decided on the type of slab. It is two-way slab. This slab is going to be a two-way slab. So we have already completed the one-way slab. So we are going to the design. Okay, so for two-way slab, as per IS code, we have the criteria that, as we already know, we usually take for beams L by D ratio as 20, 26, 7 for cantilevers, etc. So similarly for two-way slabs, as it is simply supported slab, L by D ratio is 35. Okay, so L by D ratio as per IS 456, L by D ratio for simply supported two-way slab is 35, and there is another condition to it. If the steel we are using is HYSD steel, high HYSD steel, we need to multiply with a factor 0.8. Okay, so as we are using 415 Fe 415, it's a HYSD steel, we need to multiply with 0.8. So we have L by D ratio as 35 into 0.8. Okay, so that is 28. Okay, so we have the L by D ratio. So obviously we are going to decide what? D. Okay, so we have L, and this L will be taken as shorter span as always. Okay, so in one-way slab also we took the shorter span Lx as this span because that will be the main determining factor. Okay, so in here also this L will be taken as shorter span. Okay, so shorter span, clear span in this case is 4 meter. 4 into 10 raised to 3 divided by D is equal to 28. Okay, so you will get D is equal to 142.86 mm. Okay, so we have the total depth. Okay, we are assuming it as total depth. Okay, so it has 142.84. So we are assuming and rounding it up to 150 mm depth, total depth. Okay, so we are keeping it aside. D is equal to 150 mm. Okay, so now there is an important thing. So you have capital D, overall depth as 150 mm. So now we are going to calculate small d or effective depth as always. Okay, so that will be equal to, so that 150 mm means like this. This is 150 mm. Okay, overall depth. Okay, and suppose this is the slab that we are considering. This is Lx, that is shorter span 4 meter, and this is Ly. Okay, and this is 150 mm. We will be having two effective depths, dx and dy. Why? In one-way slab we were only designing main reinforcements in Lx direction only, in this direction only, right? We used to crank this onto those side, and Ly direction was just distribution reinforcement because it was not so relevant in one-way slab. But in two-way slab both directions are important. Ly and Lx and Ly direction reinforcements will be main reinforcement. There won't be any distribution reinforcement. So we are going to design the reinforcement for both directions, considering these two as important priority. But as always, the least dimension or the shorter span will be having the priority comparatively. Okay, there will be main reinforcement here also, but Lx will be having a slight upper hand because this is shorter. The upper hand means this drawn reinforcement. These lines will in acceptance will be keeping like this, right? Cranking. So this will be the one which will be laid at the bottom. This will be the reinforcement in Lx directions. Okay, so please be careful, don't get confused. As Lx is shorter than Ly, we will be providing the main reinforcement of Lx bottommost, and Ly will be provided like this. Ly direction means like this. There will be cranking also. In both directions there will be cranking. Okay, so I hope you got the point. Lx direction main reinforcement will be provided at the bottom. That means the tension will be most taken at the Lx direction. That's why it is keeping at the most bottom portion. Okay, so Ly direction is secondary compared to its main reinforcement, but it is secondary compared to Lx reinforcement. So we will be keeping that reinforcement along Ly on the top of Lx direction or shorter span direction main reinforcement. Okay, so it alters this arrangement, alters this effective depth. Okay, so dx means the effective depth on shorter span. Okay, effective depth along shorter span means this is 150, right? Total is 150. This portion will be clear cover. That will be around 20 mm for each slab, for one-way slab and two-way slab. 20 mm, we'll assume it. Then what will be dx, effective depth along shorter span will be the midpoint of this particular bar, right? So you in slabs and beams we just used to calculate at the bottom part, right? So in this case the LX direction reinforcement is the bottom one, so we need the distance from here to the midpoint of this bottom reinforcement. Okay, midpoint. So that means LX dx is equal to d minus, that is 150, minus clear cover minus 5/2, midpoint, right? So if this is 150, we want this dimension, this is 20, so this dimension is dx, same thing, enlarged. Okay, so dx is equal to d minus c is 20 minus 5/2. 5 will be assumed as 8 as always. The most common diameter out is 8. Okay, so assuming 8, we will calculate it as 150 minus 20 minus 8/2. Okay, so that gives you 126 mm. And there is the next one, Ly, dy effective depth along longer span is equal to, what will be the effective depth along longer span? It will be from here to midpoint of this reinforcement along Ly direction, this point, dy. dy. I think this will be enough. Dy. Now I think you can just write the equation. D minus C, that is 20, minus 5, that is diameter of LX direction reinforcement, 8 minus 5/2. Right, is it clear? So we are simply calculating the distance from the topmost fiber to the midpoint of Ly direction, longer direction main reinforcement. Okay, so the value will be 150 minus 20 minus 8 minus 4. Okay, so I will give you 118 mm. So these values are important. Okay, so we'll keep it aside. So we have dx and dy. Okay, now we are going to calculate effective span. Okay, so in two-way slabs, the effective span will be always with respect to shorter span, LX span. Okay, so effective span along LX will be equal to the same criteria, nothing changes. First one is clear span plus D, that is 4 plus clear span along, we are calculating along shorter direction, so shorter span, so 4 meters plus D is 0.126 in meters, so 4.126. Second one, it is center to center distance between supports. Okay, so that was clear span plus 200 was the thickness of wall. Okay, so 0.2 by 2 plus 0.2 by 2, you will get 4.2. Minimum of these values, so we will select 4.126. So LX is 4.126 meter. Okay, then effective span along LY, that is, so L effective X, LY is the clear span, that will be equal to just the clear span. You don't need to calculate with these two criteria, just take the clear span. Clear span is just 6 meter. So we won't be using the 6 meter all that much. It's a bit irrelevant compared to 4.126. Okay, so we'll be adopting this value as primary model. Okay, so that was effective span. So we have span, effective span, and now we are going into load calculation. Same order of calculation with respect to beams or one-way slab till now. Okay, so load calculation, dead load was self-weight, that is 25 this weight density into 1 meter is the width. As always, we will be designing always for 1 meter width, any slab. 1 into total depth is 0.15, that is 3.75 kilonewton per meter. Okay, so floor finish load. Okay, so maybe in your question it would have said that in this 4 kilonewton meter square floor finish load was included. If not, you can assume it has around 1 kilonewton per meter square. Okay, so for converting it into per meter terms, because we are considering for 1 meter of width, we will multiply with floor finish load per meter, that is equal to 1 into 1 kilonewton per meter square, that will be 1 kilonewton per meter. Okay, and live load is equal to 4 kilonewton per meter square. In similar way, we will be converting it into 4 kilonewton per meter. So total load is 3.75 plus 1 plus 4, that is 8.75 kilonewton per meter. That is the total load. Okay, so in previous cases, in one-way slab or beams or anything, we will be calculating bending moment equation, substituting this load into bending moment equation. But in this case, in two-way slabs, we are getting into a different approach. We will be taking this load and multiplied with the factor 1.5 to get factored load, not factored moment. We will be calculating factored load, that is obviously 1.5 into whatever load comes here, that is 8.75, that is 13.125 kilonewton per meter. Okay, so we will keep this aside. Factored load (13.125 kilonewton per meter). Okay, now for two-way slab we will be taking a different approach than the before we have learned any types of beams or slabs. Okay, so we have all these details: dx, dy, effective span, factored load of 13.125. Refer page number 91 of IS 456. You will get mu values or bending moment values or equations for both sides. As we have 4/6 area, we need to calculate the bending moment, reinforcement for each sides. We will be calculating it separately. Okay, so we have an equation, and in page number 91 you will find bending moment along Lx, shorter span. Lx will be termed as mx, and bending moment along Ly, the longer span, always the longer span, will be termed as my. Okay, so the equations are alpha x w Lx square and alpha y w Lx square. Okay, you can just refer the IS code, that's it. Okay, so in that page itself it is referred that you can calculate this two unknown values and unknown factors from the table itself. Okay, on the same page 91. Okay, so with the help of Lx, Ly by Lx value, that was 1.5, right? 6/4 is equal to 1.5. With this value you can calculate, you can get values of alpha x and alpha y. You know what is W? W is 13.125. You know what is Lx? Lx is 4.126. Okay, so you will calculate alpha x and alpha y. Alpha x you will get from the table as 0.104. Alpha y you will get it as 0.046. Okay, so then you can calculate mx and my. Okay, it's just that you will calculate it separately. In one-way slab we will be calculating single shorter span like this with the mu that you usually calculate with single reinforced beams, singly reinforced beams, and then just avoid this calculation of Ly and just distribute minimum reinforcement as distribution reinforcement for Ly direction. But in this case, two-way slabs, as this ratio is less than 2, you need to calculate two reinforcements separately. So you need to calculate mx and my instead of single mu. Okay, so mx and my you can calculate now by alpha x is equal to 0.104 into W is 13.125 into Lx is 4.126 square. My is 0.046 is alpha y. W is 13.125 into Lx is 4.126 square. Okay, we'll get the answer as 23.24 kilonewton meter and 10.8 kilonewton meter. .218 kilonewton meter. Okay, so you have mu values of each Lx and Ly. Okay, then as always you will calculate limit values to find to compare with these values, right, as always. So mx limit is equal to same equation, no change at all, as it is Fe 415, that will be 0.138 FCK BD square. Okay, so 0.138 into FCK is 20, B is, width is 1000 into, what is D? D is, we are calculating along Lx, so dx, that is 126. Okay, same thing, my limit is equal to 0.138 FCK BD square, 0.138 into 20 into B is again 1000, D square is, D square is dy 118 square. Okay, the only change is this factor D. We have separate D values for both directions. Okay, so the answers are 43.817 kilonewton meter and 38.43 kilonewton meter. Okay, so we have limit values and mu value. So what you do next, you will just compare with this limit values with these values. Is it safe? The limit value is greater than the actual value, so it is safe. We'll continue with this factor. In this case, limit value is greater than actual moment, so it is safe. My, you can write my is less than my limit, hence it is under reinforced. Okay, so that is a statement to be written. Okay, so this is the inference. So so you have mx values and my value, mx and my value less than limit value. So these are entering values that can be used for the reinforcement design. So what you will do next, you will calculate AST, that's it. How do you calculate AST? As always with this equation in the IS code. This whole equation, mu is, while designing for separately for mx, mu can be substituted as 23.24, Fy is 415, AST you have to calculate, D will be dx, Fy will be always 415, B is 1000, D is again, in this case for Lx direction it will be 126, FCK will be 20. Okay, so you will get a particular AST value. You will be getting, obviously getting a quadratic equation with degree 2, and you will solve it in the calculator. You will be getting a minimum value as 563.08 mm square. Okay, so we have calculated AST for Lx direction. Then calculate AST for y direction in this direction. The same equation. The only difference will be D. D will be 118 instead of 126. Okay. So you will get the answer as 252.26 mm square. Okay. So I am not writing, it will be a lot heftier and it will be, we are having a little time and space. Okay. So just the same way we will be doing for single reinforced or double reinforced beams and one-way slabs. Just we will be taking separate values, separate calculations for separate longer and shorter dimensions. Okay. So we have AST values. Then obviously what we will be doing is we will calculate or check with what? Minimum reinforcement, as always. Minimum reinforcement is 0.12%. It is 0.12 by 100 into B into D. B was 1000, D is 150. Okay, that will be equal for both, right? That value is 180 m square. Okay, so we'll compare this 180 with ASTX and ASTY. Obviously, this is the minimum reinforcement. The two values should be greater than 180. Okay, as it is. These two values are greater than 180. If not, if suppose this ASTY is less than 180, suppose it was 160, then what we'll do? We will take AST2 as 180. Okay, it's like we do in all cases. Okay, there will be requirements. If it exceeds, we will be taking the requirement itself. Okay, so in this case it's safe. We don't need to alter anything. We will just take 563 and 252. Okay, so then what is the step? As in slabs, we will be calculating spacing. For spacing we have a ratio, we have a shortcut. AST by, in this case ASTX by 1000. ASTX is for 1000 breadth or width. A5 by spacing. So spacing, this is the ratio. Spacing will be equal to 1000 A5 by ASTX. A5 is same for both. We have assumed as 8 mm thickness or 8 mm diameter bar. Okay, so 1000 into pi by 4 into 8 squared divided by ASTX is 563.08. Okay, so you'll get the spacing as 89.2 mm. Okay, the same equation we will take it here. Spacing is equal to 1000 A5 by ASTY, 1000 into pi by 4 into 8 square divided by 252.26. You will get the answer. Spacing in LY direction as 199.1 mm. Okay, so you have spacing and AST. What is the diameter also? Okay, so you can check the minimum spacing also, but in this case we know it won't be handy because 3D will be always greater than these two values. Okay, so if you have time, you can write those two spacing values, maximum spacing, that should be included, and the statement is clear. We have calculated AST and spacing, therefore provide 8 mm dia bars at 85 mm center to center in LX dimension, like this. Okay, craning in both directions with the dimensions in the one-way slab itself. Okay, LX. In here, what will be? Provide 8 mm dia bars at 190 mm spacing center to center along LY or longer dimension. In here also we will be having cranking. Okay. So we have designed reinforcements. I hope it's clear. And that was designing a reinforcement. Now we will move on to shear reinforcement. Actually in this case we won't be needing. Actually you will just write it as a heading and you will just write it off, because in shear reinforcement, as we have main reinforcement in both directions, shear stress will be 2 less. Okay, and for any two-way slab itself, shear stresses will be 2 less compared to one-way slabs. Okay, and of course we are providing more reinforcements into it. Okay, so shear is not an issue in this, in two-way slab situation. Okay, so we have to decide for one-way slab, but in case of two-way slabs it's not an issue. And the next one, deflection, the last step. Check for deflection. Okay, same equation. L by D maximum is equal to L by D basic into KT into KC into K. We know these all values. L by D basic will be obtained from the IS 456 page, the one we referred in the first point, that was 35, and we need to multiply it with 0.8 because it was IFE 450. Okay, so into KT we need to calculate with the help of FS and PT. Right. So for calculation of FS, 0.58 FY AST required divided by AST provided. Okay, so we have already calculated AST required. Okay, so in this case we will all be considering LX direction only. Take note of that. We will be adopting these values as LX, and we will be taking this AST value as AST X value. The AST provided will be calculated based on the spacing corresponding to this direction, because that is the main reinforcement. It comes at the bottom. Okay, as we had decided earlier. So AST X value we know. AST provided, how can you calculate? AST provided is equal to 1000 into pi by 4 into 8 square divided by 89 was the spacing, right? Or 85 what is spacing we had provided. So we will write 85. Okay, this is the equation. Diameter of one single bar into 1000 divided by spacing to get the AST provided. So take note of that. So in beams we just must multiply the number of bars, right? So in this case actually it's the ratio of 1000 by 85. That's it. That how much bars will be there. That's it. Okay. So it can also be written as 1000 by 85. That will be the number of bars, right? 1000 by 85. In each number of each width of 1 meter slab there will be this number of this value of reinforcement side. If it is 12, it will be 12 bars. That's it. 5 by 4, 8 square. Okay. So substitute it in here. We have AST required, and PT we have it as 100 AST by BD, where D will be 126, B will be 1000, AST will be AST X. The value we have calculated and substituted is as AST required. Okay. So likewise we will calculate KT. KC will be 1 and KF will be 1. Okay. So then in this case the value was, suppose KT was 1.3, so 28 into 1.3 into 1 into 1, 36.4. This is L by D maximum. Okay, so L, this is Lx, to be precise, Lx by D provided should not be greater than this. If it is greater than this value 36.4, you will have to redesign, or you will just have to write it should be redesigned, depth should be increased. Okay, that is the inference. We will check it. Lx is 4.126 divided by D is capital D in this case. So do not get confused. Remember, in the first step we had calculated and got this D as equated with 28 and got this capital D as 142 or something. Okay, with slight difference. Then we approximated that value to 150, right? So we need to produce that value, the value that we are now providing, that is 150 in the denominator. Okay, so 4.126 divided by 150, that will give you 27, around 27. So that is okay. So Lx by D provided is less than L by D maximum, hence slab is safe in deflection. Okay, right. So if suppose if it is greater than, then you will just have to write it is not safe in deflection. You need to increase the depth of slab and redesign. Okay, that's it. Okay, so that was design of two-way slab. Okay, that two-part was the only tricky one. Everything else is similar to one-way slab and single reinforced beams. Okay, thank you.